Whether I call it dy by dx or f prime, all this time when I talk about the derivative, I'm making reference to the first derivative. Now, if there's a first derivative, I'm hoping that some of you might have assumed that there is a second derivative. So, when I say second derivative, all I mean is all you're going to do is to just differentiate it again. So you differentiate it once and differentiate it a second time. So in other words, you find dy by dx, and what are you going to do? You are going to differentiate dy by dx with respect to x, leaving you with d squared y by dx squared. That is the notation for the second derivative. So let's look at an example of how we'd find this. Let's say that we have x cubed plus 3 plus x. Y is equal to that. Let's find y prime. Y prime would be equal to 3x squared plus 0 plus 1. And y prime prime, which is the second derivative, would be equal to 6x. So we just found the second derivative. Now, we looked at finding the first derivative of a parametric equation. We looked at finding the derivative of x equal t squared and y equal t cubed. Now, to find dy by dx, we divided dy by dt by dx by dt, and we found that dy by dt was equal to 3t squared and dx by dt was equal to 2t, rendering dy by dx nothing less than 3 over 2t. Now, to find the second derivative, what are we going to do? We are going to be finding the derivative of dy by dx. So let me remind you, as we wrote on the previous page, that dy by dx is equal to 3t over 2. So when we find the first derivative of a parametric equation, we are going to end up with a function in terms of t. But we want to find the second derivative, and we are differentiating with respect to x. So how exactly are we going to differentiate a function in terms of t with respect to x? So d squared y by dx squared, the second derivative, would be equal to the derivative of dy by dx with respect to t. Now, we're just going with the flow here and see where it takes us. So, we need to intuitively, let me say that again, we need to intuitively cancel the dt and put a dx down there. But all we have is dx by dt. So what we're going to do, we're going to divide by it. Why? Because the intuition that I want you to get behind finding the second derivative of a parametric equation is that we're multiplying by, it's like we're multiplying by dt by dx, and this cancels with that, leaving us with the first derivative of the first derivative with respect to x. But that is not the case. That is merely a way for you to picture in your mind what is really happening. So let's get rid of this foolishness. And we're going to be dividing by dx by dt. So let's do that. So we know what dy by dx is. We know that dy by dx is 3 over 2 t. 3 over 2 t. Now, if we were to differentiate that with respect to t, what would you end up with? 3 over 2, because 3 over 2 is the coefficient of the t, where t is being raised to the power of 1. Now, what is dx by dt? Let's take a look back at that. Dx by dt is 2t. So let's come back down here now. And so to find the second derivative, we have to multiply, or rather divide, the differential of dy by dx, which is 3 over 2. Divide that by dx by dt, where dx by dt, as we said before, is 2t. And what's that equal to? That's equal to 3 over 4t. In other words, the first derivative is 3t over 2, but the second derivative of this parametric equation is this right here, 3 over 4t. So let's look at one final example of finding the second derivative of a parametric equation. Let's say that x is equal to the sine of 4t, and y is equal to 2 times the cos of 4t minus 1. So let's find dx by dt. Remember, the aim of this in this section is to find the second derivative. So dx by dt would be equal to, what's the differential of sine? Differentiate sine, you get cos. So it's cos 4t. And remember, chain rule says that we go in the bracket and differentiate what's in the bracket and multiply by it. Differentiate 4t with respect to t, we get 4. So we're multiplying cos 4t by 4. Now, to differentiate dy by dt, to differentiate y rather with respect to t, we're going to end up with the differential of 2 cos 4t. Differentiate cos, you get negative sine, and differentiate 4t, you get 4. So that is negative 8 sine 4t. The differential of negative 1 is 0, so that's all we have there. And then we know that dy by dx would be equal to dy by dt divided by the cos divided by dx by dt. So that would render us having negative 8 sine 4t all over 4 cos 4t. So that leaves us with negative 2. What's sine 4t over cos 4t? That is tan 4t. So that is negative 2 tan 4t. That is what is the function. That's the function that gives us dy by dx. But as we say, we don't want dy by dx, we want d squared y by dx squared. So let's find that. So d squared y by dx squared, as we said, is equal to the derivative of dy by dx with respect to t divided by dx by dt. So to differentiate the first derivative, the differential of negative 2 tan 4t with respect to t would be equal to, we're differentiating tan, you get sec squared, and differentiate 4t, you get 4, so that's negative 8 sec squared 4t. And we're going to be dividing that now. We're going to be dividing negative 8 sec squared 4t by what? 4 cos 4t. Now, remember, sec is 1 over cos. So what this is telling us here is that we're actually having negative 8 over 4 cos cube 4t, leaving us with what? Negative 2 over cos cube 4t. right? Let's clear up here. And negative 2 over cos cube for t is the same thing as negative 2 sec cube for t. So here we have it. We have found d squared y by dx squared, the second derivative of this parametric equation. So it's